Hey there. So in this video we are going to talk about graphs, graphing functions. We talked about functions and their domain and range in the last video, and now we're going to talk about graphing them. Now, I want to point out this is something that I think all of you have seen, but it's not. I think it's kind of like inventing the wheel. It's one of these things that seems obvious once you know it, but it's not. I don't think it was obvious. It clearly wasn't obvious to mathematicians for a very long time. And in fact, we didn't have graphs the way we think of them until the 1600s when Descartes came along. And let me show you who I'm talking about here. There he is. There's this handsome gentleman, Descartes. And he is the fellow that came up with this idea of depicting functions by graphs in the sense that we're familiar, by using the Cartesian coordinate system, which is named after him. So let me give you an idea of what I'm talking about here. So when we first, when we were just thinking about functions, let me open this up here, this handy dandy little app here. Okay, so one of the functions we talked about was f of x equals x squared. Okay, and now what I'm showing you a picture of, let me see if I can, there we go, I'm moving it down a little bit. What I'm showing you a picture of is both the domain and the range. So the upper line is the domain, and the lower line is the range. Okay, and so we have x lives in the domain and f of x lives in the range. Now, if I were to take the number 0 and square it, what do I get? I get 0. And that's why it's showing that 0 goes to 0, right? And if I square 1, it goes to 1. So the line just points straight down. If I square 2, however, I get 4. So you can see f of x is shifted a little bit more to the right. If I square 3, well, now the arrow is pointing all the way over to 9. Right, so as I move x around, you can see f of x move around. So this is kind of a picture of a function and how it works. For the different values of x, I can see the different values of f of x. Right, and you can see the domain, x can be anything. Right, I can choose any number for x, but look at the range. And we said in a previous video, I think it's 2 videos ago, that the range is only the numbers 0 to infinity. And you can see that. See, I cannot get f of x to go less than 0. As much as I try, no matter where I put x, f of x refuses to be less than 0. So that's why the range is all non-negative numbers, whereas the domain is all numbers. Right? So this is a picture of x squared. Let's take a look at square root of x. I think maybe I can write it like this. Let's see if it'll let me write square root as squirt. We'll see if this, no, it doesn't like that. Okay, so I'll write, some programs do let you do that. I'll write x to the power 1/2. That's the same thing as the square root. Square root of x plus 3. Okay, what's going on here? Why am I not getting an f of x when I'm down here? Well, because I'm not in the domain of my function. Remember, if you're not in the domain of your function, function doesn't make sense. I need to get this into the domain. Okay, by the time I get to 0, now I'm in the domain, so I get an f of x, right? The f of x corresponding to 0 is 3. And as I change x, I can see that f of x changes as well. And you can see how that happens. So I'm getting this relationship between x and f of x. I'm kind of getting a picture for what the function looks like. And another function we looked at was 1 over x minus 1 squared. That's another function we looked at. Here, look at this. I'm fine. I've got all these values. This is fine. I'm getting f of x. But then look what happens when I get near 1. Boom! It's gone. F of x is gone. Why is that? Because 1 isn't in the domain. There is no f of x. But as soon as I go past 1, f of x is in the domain. So I can see different values of x give me different values for f of x. So I'm getting a picture for how my function works, and it works as long as I don't put x at 1. And then as long as it's not there, I get an f of x. So look at this. This is kind of a picture of how the function is. This is kind of a picture of the function. Just by wiggling x around, I can see where f of x goes. But this is probably not the picture you're used to, right? This is not a graph. It's kind of a graph. I'm seeing both the domain and the range together, and that's what a graph does. It's a way of picturing both the domain and the range together at the same time. And up until the 1600s, this is probably how people thought about functions, what you're seeing right now. So just imagine all these mathematical discoveries that they were making, and this is what they were thinking about. It's kind of hard to think about things this way. There must be a cooler way, a neater way to view a function. And that's what Descartes came up with. He came up with the Cartesian coordinate system. He said, wait a minute, instead of putting the domain and range side by side, what if we put them perpendicular to each other? What if we took that lower line, rotated it 90 degrees, and then did the same thing? Now that's kind of a, I hope you agree, that's it's not obvious. Like, it's kind of like, what? Why would you do that? But of course we know that's how we make a graph, right? As we know them. So how do I get out of this view? So let's go do that. So instead of looking at functions the obvious, that way, that what I would call maybe the most intuitive way, let's look at functions this way. So here I've taken let me see if I can move this over. There we go. Okay, that's better. Instead of putting the axes side by side, as we had before, I'm putting them perpendicular to another. Now, okay, that's not, let me put the same function I had before at first, x squared. Now you might say, well, that's not helping any. I mean, it's just as confusing as it was before. I'm moving x and I'm seeing f of x move. Okay, but now we have a little bit more space to work with, right? Now we have not one dimension, but two dimensions. Let's use both these dimensions. Let's put a point directly above x and directly to the right of f of x. What happens here? Well, I can plot that point, and as I move x around, now look, when we trace that point out, I get a shape. And this is the point of a graph. Now, I feel like you were probably saying, yeah, I know this. I know how to draw a graph. But I think it's useful to kind of see how it actually happens and to appreciate how unobvious it is, you know, to get to this step, putting the axes orthogonally to one another, perpendicular. That's the mathematician's way of saying perpendicular, orthogonal. Doing that's not obvious. So I think this is really an amazing discovery by Descartes. You know, this is really cool. And look at this. We get this nice picture. That picture encodes the entire function. So now, instead of thinking about these weird interactions of these side-by-side objects moving back and forth, I can just draw this curve. I think that's just amazing. I think this is really cool. So just by looking at that curve, I can figure out the value of the domain element. I just go down to the bottom. And to know where that goes, I just go up to the graph and over to the vertical axis, and I know the range element. So it's almost like a map. It's telling me how to get from the domain to the range, and thus describing the function. And of course, I can draw the whole graph as we usually just draw a nice smooth curve instead of plotting all those infinitude of points, right? So that's x squared. Let's look at our other one. It was square root of x, x to the 1/2 plus 3. Let's not cheat and show the graph yet. Let's just show. Here's what it looks like if I just move the. These values aren't in the domain, but if I just move the x around, this is what I'm seeing. This is kind of what we were seeing in the other picture. But if I plot the point above x, look at this. If I plot those points for all these x's, computer has a hard time near 0. But look, I get a nice curve. Right? There we go. That looks a little better. So I'm tracing out the graph. Pretty handy dandy, right? Okay, let's take this function and see what happens. Okay, so there's x and there's f of x. What's going on here? Look at this. Hard to tell what's going on. But if I trace all the points, if I put a point above x and to the right of f of x, right? And then trace it, I can kind of see what's going on. Look at this. I'm getting a volcano. right? Zoom out a little bit. Let me see this. It goes up really high like this. What does the actual graph look like? It looks like this. Let me erase the trace. You get this curve that looks like this. And you can kind of see the problem that we were talking about in the other video where we were saying that 1 is not in the domain. You can see what happens. The graph goes up to infinity near 1, right? So one thing I want to point out is that it's very common, even mathematicians that know what they're talking about, it's very common that they'll point at the graph and they'll say, this is f of x. This is f of x. That's not correct. And they probably know that's not correct. But it's a common mistake, and I think it's an unfortunate mistake because I think it gives people the wrong idea. The graph is not f of x. Look where f of x is in the picture. F of x is on the y-axis. F of x is a number over here, right? That's f of x over here. F of x is stuck on the y-axis. That's where f of x lives. The graph is not f of x. The graph is a pair of numbers which make a point. It's the pair of numbers x comma f of x. So always remember that, even mathematicians, even people know what we're talking about, sometimes they slip and it's kind of like a verbal shorthand. They point at the graph and say this is f of x. It's not technically right. The graph is actually a set of points which have f of x as the y coordinate. Okay? So anyway, hey, I just want to pop into this video and add something. I want to mention something about domain and range while we're talking about graphs. Okay, so here's some of the functions that we just looked at. One of them was x squared over 2. F of x equals x squared over 2. And I want to talk about how you get the domain and the range by just looking at the graph. Okay, so remember that the domain is represented by the x-axis. It's usually the horizontal axis. And the range is represented on the y-axis, all right? But the domain and the range are actually subsets of these axes. It's the numbers on the axis where the domain is the numbers on the x-axis where the function actually has a value, right? So where I actually can go up to the graph and find a graph there. And the range is the set of values on the y-axis where they came from a number on the x-axis by going up to the graph and over, which means the graph has to be either to the right or to the left of a number on the y-axis for that number to be in the range. So to find the domain, I just ask which values actually have a graph above them. And in this particular function, every single value down here has a graph above it. Now, I don't see the graph above here just because the graph is too high, but I know that if I were to plug it into this function here, I would get a number out, and therefore I would have a value to pinpoint a point on the graph. So I know that the domain is the set of all numbers. So what I'm saying here is the domain, what we see is that the domain is the interval from negative infinity to infinity. Okay? What about the range? Well, not every y has an associated x. Not for every y, it's not the case that I can go over to the graph and down and find the x. For all these y's I can. For any y up here, I can go over and down and find the x that it came from. And that means that that's in the range. All right? But if I go down to here, I go to the left or the right, there is no graph. And so those values of y aren't in the range. So the range only includes the y's that start here and go up. So the range is the interval 0 to infinity. Note that I put a square bracket around the 0 because 0 is included, right? 0 does have an associated x value. When I plug in 0 for x, I get 0 for y. And so 0 is a valid value for y in the range. So I do include 0 here. So I use a square bracket around the 0. Okay. Now let's look at one of the other examples we saw. We had square root of x plus 3. what are the values, what are its domain and range? Well, the domain are the set of x values that give us a graph, right? Well, notice that x can't be to the left of 0, right? There's no graph up there. So that's not in the domain. X could be 0. That's okay. If I go 0, I can take the square root of 0, that's 0, plus 3, and I get 3, this number right here. So that's okay. So I know that the domain starts at 0. And how far does it go? It goes forever. Every single value of x to the right of 0, I can take the square root of that and add 3. So it goes to infinity, like this. What about the range? Well, now I'm asking about what y values have a graph to the left or the right. Well, none of the y values down here do, but as soon as I get to 3, I do. So I know the range starts at 3 and includes 3. And I can just keep going up and up and up, and I'll always be able to find an x that'll give me that y. So the range goes from 3 to infinity and includes 3. All right? And the other graph that we looked at was the graph for the function 1 over 1 minus x squared. What about its domain? Well, it looks like pretty much every value of x has the graph above it, so it has an associated y value, except for one spot. Look at x equals 1. If I try to plug x equals 1 into this function, what happens? Well, I get 1 minus 1 squared. That's 0 squared, and that's in the denominator. See, I'm dividing. We're not allowed to divide by 0. Dividing by 0 does not give a meaningful answer. So there is no y associated with x equals 1. But any other number for x is fine. So for the domain here, I have all numbers up to 1, but not including 1. So I use a round bracket. Together with, I use the union symbol, all numbers from 1 to infinity. Notice I've got all numbers here, but I skipped over 1. 1 is not included in this interval, and it's not included in this interval. So I've got all numbers except 1 in the domain. What about the range? Well, the range are the set of all y values that have the graph to the left or right. Well, all of these numbers have a graph to the left or right, except, until I get down to 0. Is there a graph to the right or left of 0? Well, it's hard to tell by looking at the picture, but if we go back up to the function, I would have to be asking, is there a value of x that I could plug into here and get 0 as an answer? And look what we're doing. We're taking 1 and dividing by some expression of x. Can I divide 1 by something and get 0? No, it's impossible. You can't divide by something and end up with 0. That's not possible. So that means that 0 is not in the range. But every number greater than 0 is. So here we have to use a round bracket around 0. Okay. I want to point out one other thing with graphs. When we draw a graph, and graphs can look pretty crazy, they can be pretty wiggly and wild. When I draw a graph, we use either a solid dot or an empty dot to denote whether or not that point is actually on the graph. So this point is on the graph. This is on the graph. This point is not on the graph. So the graph goes up to this point, but never actually gets there. And that's why we use an open circle as opposed to a closed circle. So if these were the numbers, say 1 to 9 down here, and this went up to the number, let's just go over to the right here, suppose that was 8. If I was looking at the domain and range of this function, I need to figure out what this is. Let's say that's the number 1. Okay, so I got numbers up to 8 here and up to 9 here. If I was looking at the domain and range here, what would I be looking at? Well, the domain are the set of x values that have a graph above or below them, right? Well, 1 does not, because that point's not on the graph. But as soon as I go to the right of 1, I do hit the graph. So the domain starts at 1 but does not include 1. And it goes up to 9, and it does include 9 because this point is on the graph. So I use a square bracket around 9. So that's my domain, the open interval 1 to 9. Well, it's open on the left, closed on the right. The range, well, can I go below 1? Well, no, there's no graph below 1. But can I get to 1? Yeah, I can get to 1 by hitting this point right here. I know this point is on the graph because if it weren't, I would have had to have drawn an open circle here. Since they didn't draw an open circle, we know this point is actually on the graph. So 1 is hit by the graph. So 1 is in the range. Just to reiterate, if it weren't, there'd be an open circle here. And how high can I go in the range? Well, all these values, you might say, well, wait a minute, this value is not in the range because there's an open circle here. And you'd be right, except that I can go through that and hit the graph over here. So there really is an x that gets me to that value. It's not here, it's not 1, it's actually over here. It's whatever number that is. All right, so there is a number that gets me to there. So this is okay. Even though there's an open circle to the right, it's okay. As long as I can find some graph to the right, I'm good. And I can keep going up until I get to 8. And 8 is in the range because this is on the graph. So I go up to 8 and it includes 8. So you can get any variety of open or closed brackets on these intervals depending on the shape of the graph and whether it has open or closed endpoints. So keep that in mind. It's something you have to be careful about. Okay, so I just wanted to jump in here and make these statements about domain and range, and now I'll return you to White Shirt Andrew, and he'll finish up the video. This is graphing, so I just wanted to point that out to you, introduce you to Descartes, and well, that's it. I'll see you in the next video.